Okay, now 3D. Curve and divergence of the vector field, but in 3D. The formula is a little bit more complicated. Let me start for divergence first. Divergence of the vector field. Well, vector field, okay, suppose que have three components because 3D, PQR is the first component, the second component, the third component. Okay. Now divergence is partial derivative x, partial derivative p with respect to x, plus partial derivative q with respect to y, and plus partial derivative r with respect to z. It's easy. This is similar to 2D. But curve is different, totally different. Because first of all, a curve, the answer is no function. Well, it's a function, but it's vector value function. It's a vector. And the formula is ry minus qz, comma, pz minus rx, comma, qx minus py. This is the first component, the second component, and the third component. This is very, very hard to memorize that formula. So I propose you one convenience notation using nabla. Remember, nabla is the symbol that we are using for the gradient, nabla f. But nabla, like a symbolic operator, is partial derivative with respect to x, comma, partial derivative with respect to y, comma, partial derivative with respect to z, like a vector, no? But partial derivative of what? What you put it here in the front. Suppose partial derivative of nabla f indicate partial derivative f with respect to x, comma, partial derivative f with respect to y, comma, partial derivative f with respect to z. And this is a very well known formula for the gradient. The way you study the test 2, no? We're using this notation, nabla notation, to represent divergence and represent a curve. How? Well, let me show you. It's super fantastic. Look. See, you perform a dot product. This is symbolic dot product between nabla and capital F, que es the vector field. It's a dot product. So the answer is a scalar function. And the scalar function is, suppose, this is partial derivative with respect to x, comma, partial derivative with respect to y, comma, partial derivative with respect to z, of what? Dot product, PQR. And remember the idea for the dot product, your multiplication, this and this, this and this, this and this, component by component. Entonces, partial derivative of p with respect to x plus partial derivative q with respect to y and partial derivative r with respect to z. And it's exactly the same, this formula. It's present, different notation, but it's the same. Entonces, dot product, nabla, dot product f represent divergence. So, conclusion, divergence of f is equal nabla dot product f. Wow, I like this notation. And curve is more complicated because it's cross product. Suppose I perform now the cross product between nabla operator, cross product f. And remember to compute the cross product, we use the term ijk. I put here partial derivative with respect to x, partial derivative with respect to y. This is totally symbolic, right? Partial derivative with respect to z. I put it here PQR. Okay, let's do it. let's do it. Expand this determinant as always using the first rule. This I, multiplication something. Multiplication, you delete this and this. This is partial derivative R with respect to Y. Look, let me write in this notation. Minus partial derivative Q with respect to C. This is the first component. Look, this component is this component. Minus J, remember it's negative. Minus J, delete, delete. This is partial derivative of R with respect to X minus partial derivative B with respect to C. Wow, this is weird because this is completely opposite side to this, no? But you have a minus in the front. Okay, so it's the same. Exactly the same. Finally, plus K. And plus K, you delete this column and this column. Just stay partial derivative Q with respect to X minus partial derivative P with respect to Y. It's exactly the same of this formula. Conclusion, in this convenience notation, nabla cross F represents a curve of F. This is another notation, new notation, using nabla operator. The new thing that brings me 3D is that the curve of the vector field now is a vector. And this vector, let me try to understand this vector. This vector, suppose this is a point in 3D. And the vector field is like that. Then this vector, que is a curve, is a vector, in this case, is in that direction, using the right hand rule. Suppose you using this finger to see the vector and the thumb point to the up. Okay, right rule. Hand right rule. Indicate the direction of the vector. Si es positive, the rotation is counterclockwise. Si es negative, clockwise. No vector, null vector, in this case null vector is different to 0. Null vector is 0, 0, 0, null vector. We have no direction, no rotation. No rotation. And by the way, the absolute values of the magnitude of the curve of F represent twice the angular velocity, so omega, twice 2 omega, que rotate this vector field. Omega is angular velocity in radian per second. Okay? Let's see example now.